Welcome to Derivatives Problem Examples Part 2. All right, again, this is review from Part 1 and the previous sections. If y is equal to ax raised to the n power, then dy dx is equal to a times n, x raised to the n minus 1 power, y is y, x is x. A is the number in front of x, and n is the exponent. Okay, so if we get a question that's asking for f prime of a for the function, so question 1, we're given y equals 3x squared plus 2x minus 1 with an a equal to minus 1. What that's saying is when you find the derivative, you're finding the slope of that function. But because we're talking calculus and curvy stuff, we need to pick, if we want to know the instantaneous slope at a specific point, we change that designation as f prime, and in this example, f prime a. So it's asking for a specific slope at a specific x, if you would, and a would be that specific x. So the first step is to go ahead and take the derivative. That gives us dy dx of the function. And we get a dy dx, and you can follow the math there, of 6x plus 2. Okay, so now in order to do the f prime for that equation, we're going to instead of saying dy dx, because now we're talking about a specific slope at a specific point within the function, we're going to change the terminology and say, okay, well, now we're talking f prime. So dy dx becomes or is equal to f prime, and I like to put the little subscript there to know which x we're talking about. So f prime at an x equal to negative 1 now equals 6x plus 2. Well, that x equal to negative 1, we'll drop that in for the x. So we get 6 times negative 1 plus 2. So we get an f prime at negative 1 is equal to negative 4. So what that's saying is at that point, we've got a slope equal to negative 4. And if we zoom in, so up here I've got graphical analysis using Desmos of the original function, right? And you can see that parabola. And then now we're talking about points of where x is equal to minus 1. So if you look at the x-axis and minus 1, I've zoomed in really tight. And this is what they used to do to figure out the slope of a curve way back before they discovered calculus. So what they do is zoom in on the slope really, really tight to where that slope almost looks like a straight line. And in the below graphic, I've zoomed in on that function. You can see where it almost looks like a straight line. And so what I've done is I'm zoomed in so much I can kind of say, okay, well, that looks kind of straight, and that's going through point 1. And I'm not exactly doing it perfect here, because ideally I'd be up above equal amounts and below equal amounts from that point x equals negative 1. But I looked and I saw, okay, well, there's a point and there's a point, the blue point and the green point, where it crosses a major division. And I can see that I've got a y traveling left to right. I've got a y of negative 4, 1, 2, 3, 4 major gradicules, and an x of a positive 1. So if I say delta y over delta x, that would be minus 4 divided by a positive 1, which is a way that I can spot check my f prime. And both those numbers equal negative 4. Here's question number 2. And again, we're looking for another f prime. And it's just a different way of asking the question. They're saying find the equation of the tangent line to the curve. Well, the curve is y equals x to the cubed power plus 4x to the squared power minus x plus 2. And then they're saying at the specific points x and y, minus 2 and 12. Well, the tangent line is the slope at those points. So we can tackle this problem the same, pretty similar to the previous. So we're going to take the derivative of the original function, and then we're going to go ahead and do the f prime, where we're going to, once we've got the derivative, we can now put in the value of -2 for the x's, and then solve for the f prime at a -2, and we get -5. So in order to spot check that, I've got the original function here plotted in Desmos, and you can see that kind of, you can see the cube. That's kind of what happens when you get an x cubed in your formula. And I've zoomed in at the point where x is equal to -2, and that's the below graphic there. It's zoomed way in at that x -2 and comma 12. So x -2 is equal to y equal to 12. So it's the exact point that they gave us in the original equation. If we zoom in enough, we can get that to look almost like a straight line. So we're just going to spot check it, and if we look at it, it is going negative. And if we count up all the minors on the y scale, I count a -20, and then from there over, it's got a positive x of 4, and you do that math, you get the -5. So that is the same as our f prime number. So we're getting a -5 is our slope at that point, -2, comma 12. Okay, so, but that doesn't really, that just gives us the slope at that point. It gives us the slope of that line. It doesn't define the line. And the original question asks for the equation of that tangent line. So that gives us m of the line. Okay, so the slope of that line. So now we know that that line tangent to that point would be y equals mx plus b. We've got an x and a y given, and we've now got the slope. So now we can solve for the b, the y-intercept of that line. And you can see the math here. We just put in all those values and we get a b equal to 2. So now, therefore, the equation of that line, we're going to turn around and put the slope in and the y-intercept, and then leave our y and our x as variables. So that defines that line right there, y equals -5, x plus 2. And that is the final answer. That's what they're asking for in this original question. So here is like a question, like a second semester question, but we're going to solve it using calculus. So if power is equal to resistance times current squared, I squared R, find the rate of change when R is equal to 30 ohms and I is equal to 2 amps. So most of it, like second semester, we would just go ahead and just take I squared times R. So 2 times 2, 4 times 30 is 120 watts, right? So, but if we wanted to do this using calculus, we could take the derivative, and because the p is in the y location and the squared component is the I, you could think of that as delta y, delta x right there. So you've got a dp di, and we're going to take the derivative of that. So that gives us a 2. Think of r as the number in front. So 2r, and then we've got an I raised to the n power -1. So I raised to the 1 power. So our dp di is 2ri. Now, if we want to find the specific power at that point, we would drop in our r and our I, which gives us 2 times r times I, which gives us the same answer that we calculated using the second semester way, 120 watts per amp at that point.